right, you might notice a little bit of a glitch. I had my video cut out, and so we need to kind of start over with B, so you'll see some scribbles over here. So in part B, it asked me to calculate the molar mass of my unknown metal M. And in this particular case, I personally think that the way that they showed on the answer key is a little bit more complicated than the way that I would do it. So I'm going to show you how I would do it, and you can kind of follow along with the answer key and decide which one makes the most sense to you. So what I know in my problem from my data is that my overall compound Mi2 weighed 1.284 grams. So if I am thinking to myself, hey, I want to find the molar mass of M, right now my M is trapped in Mi2. So maybe if I figure out the molar mass of M, I could then take out the mass of the iodine and figure out the M on its own. So right now I know that my mass of Mi2 is 1.284 grams. So that's how much that weighs. Okay. From my previous problem as well, I know how many moles of I2 were in my reaction. And based on my equation up here, if my 0.004 moles of I2 are going to turn into the same number of moles of Mi2 because of the 1-to-1 mole ratio. So what I'm going to do is I'm going to take my grams of Mi2 and divide them by my 0.004023 moles of Mi2. And again, this is different than what the answer key shows you, but it's going to lead you to the same answer. So what I figure out in the end is that it's 319.16 grams for 1 mole of Mi2. So that's the molar mass of that whole shebang. But I know that I just did the calculation for the iodine's molar mass. And if I take away 253.80 grams for my iodine, I am left with a mass of 65.36 grams. Now, like I said, I know on the answer key, they show you some stoichiometry where they find the mass of the metal first, and then they divide by the moles of the metal. It's kind of the same thing, but for me, I like this a little bit better because I don't have to do any fancy math before I do the moles and grams division, and then I can move on from there. Hopefully that makes sense to you. All right, moving on to C. The student hypothesizes that the compound formed in the synthesis reaction is ionic. Propose an experimental test that the student could perform to support the hypothesis. Explain how the results of the test would support the hypothesis if the substance was ionic. So there are some different things that you can do to talk about or to say if something is ionic. There are a couple different things. You know that if it's dissolved in water, it's going to conduct electricity. Okay. The same thing conducts electricity when it's melted. And the other thing we know about ionic compounds is that they have incredibly strong bonds that are holding them together. So that would give them kind of freakishly high melting points. And we're talking like unusually high melting points. So all of those things are going to be potential tests that you could run. You could dissolve it and see if it conducts electricity. You could melt it and see if it conducts electricity, or you could test its melting point. And in all of those things, if it conducts electricity in either of these phases, that's an indication that it's an ionic compound, and the same thing for a melting point. So any of those discussions are fine. And lastly, for D, it says the student hypothesizes that Br2 will react with metal M more vigorously than I2 did because Br2 is a liquid at room temperature. D says, explain why I2 is a solid at room temperature, whereas Br2 is a liquid. Your explanation should clearly reference the types and relative strengths of the intermolecular forces in each substance. In this case, because it's talking, it tells you to talk about both substances, that's a big tip off that you're going to have kind of a 2-point problem. So you need to talk about the intermolecular forces in iodine and bromine and then talk about why they're different. Now, if you think about it, iodine and bromine are both just plain elements. So the only intermolecular force they both have are London dispersion forces. So I'm going to write the only IMFs in I2 and BR2 are London dispersion forces. And I would say it is okay to abbreviate London dispersion forces. I would not abbreviate dipole to dipole. I would write dipole to dipole on there, but H bonding is okay. I don't know why dipole to dipole is so weird, but it is. So the only two intermolecular forces in those two are London dispersion forces. And what that means is that the London dispersion forces in iodine must be stronger than bromine because I2 remains a solid at room temperature. Okay, so I've talked about how they both have London dispersion forces, and I've talked about how the properties that they've talked about in the prompt have indicated that the iodine has stronger intermolecular forces because it remains solid. And now I need to seal the deal with saying why it's that way. What's happening in this case is I2 has more electrons than Br. And that makes I2 more polarizable. It's that magic term that we talked about. So, which makes, sorry guys, it's hard to write and talk. I2 has more electrons than Br2, which makes it more polarizable than Br2. This stronger induced dipole caused by the electrons makes I2's intermolecular forces stronger. So you've got to talk something about those. Really use the more polarizable term and then talk about how it ties back into the intermolecular force property that they're talking about. All right, hopefully that clears things up. If you have any questions, let me know.